Welcome everyone to Solar Turbines webinar today on the subject of centrifugal compressors, principles, design, and control, as well as celebrate a very exciting book release titled Introduction of Centrifugal Compressors for Oil and Gas Applications, authored and edited by our keynote speaker today, Dr. Rainer Kurz. So you should see a poll in front of you on the screen. And looks like we just want to get an idea of what our audience today, what kind of compressors are you most familiar with? It looks predominantly to be centrifugal, which is great news. You're going to learn even more about them today from Rainer. And we're very excited to have you all join us today. As part of registering for this webinar, you will receive a digital copy of Rainer's new book, as well as be entered into a raffle for a signed hard copy by the author himself. And you should be notified by the end of the week. So let's go ahead and jump into it. I'm going to share my screen to kick us off. So just one moment, please. Okay, great. All right, so as mentioned, here's the subject of our webinar today and our keynote speaker, Dr. Rainer Kurz. Thank you for joining us. This is actually our fifth in a series of webinars with Rainer, so we're so excited to have him back again. So let me advance here. Again, welcome. I give you a warm welcome today, and thank you for joining us. From wherever you are in the world, from numerous backgrounds and time zones, we really appreciate you spending your time with us. My name is Danielle Robles, and I've been your moderator through this series. I've been with Solar for nearly 17 years in a variety of roles, from engineering, project management, market analyst, and today is the manager of strategic analysis in our marketing and product strategy team. In addition, I lead the project strategy team and our research and engineering enterprise process for prioritization and balancing our short and long-term investments in a mixed portfolio of products and services to make solar turbines grow and our customers successful. So let's take a look at a couple housekeeping items before we begin. For the webinar, this will be made available on our website, www.solarturbines.com. And as you saw from the very beginning, we'll be using live polling during this webinar. A link should appear in the chat when it's time to begin engaging in a poll with us. Or if for whatever reason you don't have that up in front of you, you can always type in pollev.com/solar poll. So throughout the presentation, we will take time to pause for Q&A, and it will be live and engaging for you after each section of material presented by Rainer, and take live questions from our audience. We have a very helpful team in the background who's making all of this possible today, who are promoting your questions directly to the live feed. And we will likely not get to all of the questions, but keep them coming. And if you'd like us to follow up with you, please do include your name and contact info, and we can make sure to follow up with you later. You also have the option of remaining anonymous through the live chat as well. But we do encourage you to type in your questions and engage with us and ask Rainer what you'd like. For any issues or concerns with connectivity, please do reach out to us at webinars@solarturbines.com. So let's go over a brief overview of Solar Turbines. As you can see here in the infographic, Solar Turbines is the world's largest manufacturer of industrial gas turbines in the 1 to 23, soon to be 29 megawatt space with the introduction of the Titan 350. And we started manufacturing them back in the 1960s. We've sold over 16,000 turbines, 6,800 compressors into over 100 countries. And one thing I always love pointing out is the key differentiator of our customer-focused, diverse global workforce of over 8,000 employees, many of whom are in your own time and space, with 65 sales and service locations worldwide. Here's a snapshot of our Solar Turbines gas turbine family, ranging from our 1.2 megawatt Saturn to our very new Titan 350, as you can see here. Additional information on any of these ratings and engine capabilities can be found directly on our Solar Turbines website. Also here, and the highlight of today, is our summary of our gas compressor family. We have a lineup of pre-configured compressors for both, as you can see, the oil and gas production application, where high pressure ratio is needed, and gas transmission with typically higher flow and lower pressure differential. Our solar produces currently more than 150 new gas compressors and performs over 200 compressors overhauls on an annual basis. We see significant future growth in the upstream and midstream sectors for our oil and gas industry, and our compressors are optimized to meet the demands of these market segments. Finally, here is a lineup of Solar's complete package lineup configuration. As you can see, solar gas compressors are developed to match our Solar's line of gas turbines, forming our compressor set package, as you can see here. Also available as mechanical drive. Solar's compressors have been successfully applied in a number of electric motor-driven EMD applications as well. Seen here is our Spartan EMD compressor set. And finally, we have our generator set package right in the middle, seen here optimized for oil and gas. And many of the design features support specific needs of field applications in the oil and gas industry, with an emphasis on rugged and reliable, yet flexible designs with state-of-the-art aerodynamic and rotor dynamic performance. Again, please see our website for more information on any of our package lineup. And with that, it is truly a pleasure to introduce our presenter and accomplished author, Dr. Rainer Kurz. Rainer is the manager of gas compressor engineering at Solar Turbines Incorporated here in San Diego, California. His organization is responsible for design, research, and development of solar gas compressors, which encompasses aerodynamic, rotor dynamic, and mechanical design. Dr. Kurz attended the university in Germany, where he received his doctorate in 1991. He joined Solar in 1993 and has held his current position, previous position since 1995, a total of 28 incredible years at Solar. Dr. Kurz was elected the ASME Fellow in 2003. He's authored numerous publications on turbomachinery related topics with an emphasis on compressor applications, dynamic behavior, and gas turbine operation and degradation. Many of his publications have been considered of archive quality and have accepted into publication journals and engineering journals. He has received several Best Paper and Best Tutorial Awards at the ASME Turbo Conferences and was a recipient of the 2013 ASME Industrial Gas Turbine Technology Award. He is a longtime member of GMC Organizing Committee and the GMRC Project Supervisory Committee, as well as the Turbo Symposium and Asia Turbo and Pump Symposium committees. One of his most recent accomplishments, and what we are here to celebrate today as well, is the release of his new book mentioned earlier, Introduction to Centrifugal Compressors for Oil and Gas Applications. As author and editor, Rainer, congratulations. Thank you for your commitment and contributions to this industry and to Solar Turbines. With that, let's hand it over to Rainer and he can get us started on our content. Thank you, Rainer. Can't quite hear you yet, Rainer, if you're still on mute.
Okay, can you hear me now?
Yes.
Okay, well, good morning or good afternoon or good evening, everybody, and thanks for joining us. I first of all want to thank Danielle for the kind introduction. I was always fortunate enough that, you know, you start at some point in time of your life in a certain industry and all of a sudden it's almost 30 years later and you've done a lot of interesting things. What I want to talk today is give you a little idea on centrifugal compressors. What are their working principles? How are they designed? What are the components and how do we control them? So from that, again, I will, or in addition to that, I also will talk a little bit about how do we size these machines and what kind of configurations do we find in our industry? So with that, let's look a little bit first into a cross-section of a typical centrifugal compressor. This is a barrel-style machine. So we have the blue parts, which are the pressure-containing parts. So that's the casing. And in this casing, we have a rotor with the impellers, that's in purple, and the stationary parts with the inlet, diffusers, return channels with return vanes, and a discharge volute. So essentially the gas flow goes from the inlet through the impellers, diffusers, all the way out on the discharge volute. So that's sort of the aerodynamic design, and one of the key features of this kind of compressors is that you can actually remove the end cap, and then you can slide out the entire aerodynamic parts in one piece, so you don't have to disconnect the compressor from the piping if you have to restage or revamp that machine. On the mechanical side, we have our shaft with dry gas seals on either side that prevent the pressurized process gas from leaking along the shaft. We have a thrust bearing that takes up the axial load that the impellers are creating, and journal bearings that essentially carry the weight of the rotor. Now let's talk a bit about the impellers. This shows a typical impeller for a centrifugal compressor in the oil and gas industry. So we have the hub of the impeller, and in our machines, the hub also forms part of the shaft. And then the vanes, so these are basically the airfoils that do all the aerodynamic work. And then we have the impeller shrouded, which really allows very nicely to control clearances and leakages. Now, since we compress compressible gases, the actual volume of the gas from the inlet to the compressor to the discharge of the compressor is actually reduced because we compress the gas. So therefore, we start out with higher flow impellers, and then as we go through the compressor and the flow becomes smaller, we get to lower flow impellers. These impellers can be made in a variety of different ways. We use a lot of cast impellers, but we also use 5-axis milled impellers, both 5-axis milled in a single piece, or with brazed shrouds, and there are also other manufacturers in the industry that use welded shrouds or that make open-faced impellers without a shroud. In much older machines, there are also welded impellers used. They are also often referred to as 2D impellers because the blades in these older machines lack the three-dimensional twist that allows us to very much optimize the aerodynamics. We also find impellers made with additive manufacturing, with essentially also machines where the blade channels are eroded, and then really, really old blowers where the backside, the vanes, and the shroud are riveted. So after the impeller, we have a diffuser, and there are again different types in use. The most common used diffuser is the so-called parallel wall or vaneless diffuser, like this one here, but there are also machines with wedge-type diffusers where the diffuser has distinct wedge-like channels, and low solidity, so-called low solidity diffusers, where you basically have airfoils in the diffuser. The individual impellers are put together to a rotor, and these rotors vary largely in sizes. So I've in this picture shown a rotor for our smallest machine, the C16, which is about a 7.5-inch impeller diameter, compared to one of our bigger machines, where the impellers have a diameter of over 23 inches. One of our specific way of making these rotors is that we make so-called modular rotors. This design is, by the way, fully accepted by API 617, and it's also fully accepted by our customers in the oil and gas industry. And the idea is fundamentally that each impeller has a hub that actually forms part of the shaft, and then the entire assembly is held together by a tie bolt that is held by a stub shaft on the suction and the discharge side. So the reason why we're doing that actually is that design makes restaging the machine, when after many years of service the operating conditions change to the point that it's advantageous to modify the aerodynamics, it makes that restaging very fast, very economically attractive. Now, you may remember one of the earlier slides where I showed how the bundle, which is the aerodynamic, stationary, and rotating parts, are can be moved in and out of the casing. So this picture here shows such a module or bundle, and this is the casing or center body that this bundle can be inserted. And you can see that essentially I can move the bundle in and out without having to disconnect the casing from the piping. I also mentioned in one of the earlier slides that we have dry gas seals on both shaft ends to prevent the gas from leaking along the shaft. And that's actually a very important part, because especially in the current conditions where we want to avoid leaking natural gas into the environment, the dry gas seal gives us the capability to very much minimize the amount of leakage or avoid the leakage by capturing the gas and recompressing it. So again, you remember one of the earlier slides, we have dry gas seals here and here. So dry gas seal, as you see here on the right, basically consists of a rotating ring and a stationary ring. And one of the rings has some very small grooves. If the machine does not rotate, these rings are pushed together by a spring. But as soon as the machine starts to rotate, the small leakage across these rings through these grooves generates a force that pushes these rings apart. So now we are able to operate the machine up to full speed with very minimal clearances in these rings and very, very small leakages. So essentially, the force of the gas is used to essentially oppose the closing force from the spring, and that allows us to operate the dry gas seal with a very small gap and very small leakages. So with that, we come to the first Q&A break. We now have time to answer a few questions.
Fantastic, Rainer. Thank you so much for the introduction to centrifugal compressors to begin. We do have a few questions that came in earlier from our audience members. Thank you so much. Rainer, let's go ahead and start with one that you haven't had a chance to expand on, but Do impellers and diffusers have to be custom designed for each project?
That's actually a very good question, and there's a lot of discussion in the industry. We have taken the path that we pre-design essentially the entire stage. So in our design, we match the impeller with its diffuser, and we do all the design before we actually offer the machine on a project. So that means we're not customizing these stages for a specific project, but when we make a new compressor model, we design a sufficient amount of these stage combinations that allows us to cover any possible application for that particular compressor.
That makes sense, Rainer. Thanks for expanding on that. Let's go ahead and ask a question a bit about the bundle. Can you actually remove the bundle in one piece in our compressors?
Yes. The idea is that you leave the casing connected to the piping, and then you slide out the entire bundle in one piece. Now, that does not mean that you cannot service the seals and the bearings separately if you so desire, but you can take out the entire bundle in one piece.
All right. Thanks, Rainer. That sounds very efficient in the field. A bit about seals then, another question that came in from earlier. How long do dry gas seals last?
Well, the neat thing about dry gas seals is it's a non-contacting seal. So there is no mechanical contact between the seal faces. So technically, they have an infinite life. And in fact, I've recently was at a conference where they showed a dry gas seal that they took out of a machine like after 23 years, I believe, of operation, and all they had to change were some O-rings. Now, the proper operation of a dry gas seal depends very largely on the system that supplies the seal gas into the seal. The seal gas that we're using is essentially process gas that we filter and clean before we feed it into the dry gas seal. And if that is done properly, meaning if we can keep the dirt and the liquids out, then again, there is really nothing that limits the life of a dry gas seal.
All right, thanks for expanding on that, Rainer. Our last question that came in from earlier that I think pertains to this section is when solar uses the modular designs that you touched on, most other manufacturers use a solid shaft. Can you expand on our decision for modular design in the shafts?
Yes, and it's actually a quite interesting question because you're absolutely right. Most other manufacturers use a solid shaft and shrink or key the impellers on that shaft. Although in the last few years, there are one or two other manufacturers who found the advantages of our design and are now trying also to build rotors on that principle. Historically, Solar started out as a gas turbine manufacturer, and this is basically how you build gas turbine rotors. And when we started to build compressors, we found that using this modular design gives us a tremendous advantage if we have to restage the machine, or if during the operation just one or two impellers get damaged. We can react, having that modular rotor and having standardized parts, we can react extremely fast and extremely efficient in situations like that, and that ultimately helps the amount, the availability of these machines.
Wonderful. Thanks for expanding on that, Rainer. We're doing great on time. I think you can go ahead and move on to your next section. Thank you.
Okay, thank you. Okay, so I'm going to talk a bit now on how does gas compression work, and a lot of the explanations in this section actually apply to any type of compressors that can be used to compress gas. So essentially, the general idea is if I trap gas in a certain volume, and then I reduce the volume, then I will increase its density, but I also will increase its temperature unless I basically cool that cylinder. So meaning unless heat is exchanged with the environment. And the relationships between pressure, temperature, and densities are essentially covered by thermodynamics laws about the gas. And again, that general idea applies to both centrifugal and reciprocating compressors. So what we do in a compressor is essentially we take mechanical work and convert that mechanical work into pressure and a temperature rise in the gas. So the mechanical energy or work is used to increase the energy of the gas, which shows up as an enthalpy difference. So enthalpy is a thermodynamic concept that describes the amount of energy that I feed into the gas. And that's basically the equivalent to the mechanical work that I put into the gas. And this increase of energy in the gas shows as an increase in pressure and temperature. Now, when I talk about work, then I can also state that if I take the mass flow of gas through the machine, multiply it by the work that I put into that gas, then I get the power that I need at the compressor shaft. And in this compression process will be losses. Now, these general principles can be very easily summarized for ideal gases. So I have a very simple relationship between density, pressure, and temperature. I have also a very simple relationship between work or enthalpy difference, temperature rise, and a constant that depends on the gas. Problem is that the gases that we're compressing are typically not behaving as ideal gases, they behave as real gases. And as you can see there, the relationships become a tiny bit more complicated. So on the density calculation, I add a compressibility factor, but unfortunately this factor is depending on pressure and temperature and the gas in itself. And then the work temperature relationship now also becomes a bit more complicated because that heat capacity here is also a function of pressure and temperature of the gas. So a quick word about this compressibility factor, which is basically a correction factor that corrects the density that you would get for an ideal gas in a compression process to the density that you actually get for the real gas. In most of our applications, it's typically less than 1. And that basically means that for a given pressure and temperature, the real density is a bit higher than the ideal density, which is a good thing. Now, in thermodynamics, and I'm full well aware that thermodynamics is usually one of the less favorite classes in engineering, so I'll keep this relatively short. But we can, for any gas, draw what's called a Mollier diagram that shows pressure and enthalpy. And in this chart, we have lines of constant temperature, lines of constant density, and lines of constant entropy. So basically what that means is, as soon as I know any two of these, pressure and temperature, for example, then and I know what gas I'm dealing with, then I can calculate enthalpies, I can calculate entropies and densities. And as you can see, this is a Mollier diagram for methane. And actually, methane behaves like an ideal gas as long as you're relatively low in pressure and high enough in temperature. Our machines, however, in the oil and gas industry tend to operate up here, so where the gas shows real gas behavior. So we have to treat it as a real gas. And basically, what I can show in this diagram is the compression process. So I have a starting point here defined by a pressure and a temperature. And then I know that I want to compress the gas to a certain pressure, so somewhere on this line. Now, if I haven't built the compressor yet, then I don't know exactly at what temperature I'm going to end up in that compression. But if I assume that I have a perfect compressor that is capable of doing an isentropic compression, meaning compression without any losses, then I simply follow the line of constant entropy, and I get to my end pressure at a certain temperature. And the difference between the enthalpy at the starting point and the enthalpy at the end point, that's my isentropic work. Now, once I built the compressor and I put it on the test stand, I can measure at the end point both pressure and temperature, and I can determine what is the actual enthalpy rise for that machine. And then the ratio between the two, the ratio between the isentropic enthalpy and the actual enthalpy, that's my isentropic efficiency. There are also some other efficiencies defined as a polytropic efficiency, which basically uses polytropic work instead of isentropic work. And I will not go into details in the definitions. It's just a different type of work that I use as a reference. I do want to point out, though, that the actual work, that's the part that directly translates when I work it, multiply it with the mass flow, that directly defines the power that I need for the compression. So now I showed this Mollier diagram for methane, and you will rightfully tell me, well, we don't compress methane, we compress gas mixture. So there is all sorts of other stuff in there. There's ethane, propane, heavier hydrocarbons, there is nitrogen, there's CO2, and there's all sorts of other stuff. So do we have to create a Mollier diagram for each individual gas composition? Well, fortunately, there's something that's called equation of state. And essentially, it sort of works like this Mollier diagram, except that I can write that or can determine the variables in that equation of state simply by knowing what the gas is. And then I can, just like I showed before in the Mollier diagram, I take pressure and temperature, and the equation of state tells me enthalpies and densities and things like that. Now, in the industry, there are a number of these equations of state in use. And so you may ask yourself, okay, what's the best one? So I just showed here for a specific example with a certain gas composition, certain pressures and measured temperatures that I then enter into this equation of state, and I compare the results. So I've compared a Redlich-Kwong, a Lee-Kessler-Plöcker, Benedict Webb-Rubin, Peng-Robinson equation of state, and as a reference, I use a program that's called RefProp. It's it's essentially was created by NIST, and it's sort of it's a very good reference. Now, what you see is if I compare actual work and isentropic work, there is very little difference between the different equations of state. If I use these different equations of state to calculate efficiency or to calculate density, I've just made this a bit brief by using the compressibility factor. You see there are some differences, but even on efficiency, I tend to be within a percent or so between the calculated efficiencies by the different equations of state. So the point I'm trying to make is here that if you want to compare data, just be consistent with the equation of state you use, but most equations of state that are used are reasonably accurate. Okay, then a little bit about flow. So we deal with actual flow and standard flow. And that sometimes causes a little bit confusion. Actual flow is essentially the amount of cubic feet per minute that the compressor actually sees, whereas the standard flow is the volume of gas that this gas would have if it were at 14.7 pound and 60 degrees. So you see that on that graph, the standard flow is essentially based on what the volume of the gas would be at the standard conditions, whereas the actual flow is the volume that that gas takes at the conditions at the inlet of your compressor. So with that, we come to the next Q&A break.
All right, Rainer. Yes, great section. And again, we're doing great on time. We're about 5-ish minutes to take some live questions from our audience. You can see here, for those on the line, a number of them are starting to be published. And I see many of you have been utilizing the thumbs up to tell us that you're interested in it. So please keep that up when you see those published questions come in. So Rainer, we're going to start off a question that has to do with our seals, not specifically the content you just presented, but what can solar turbines help our customers with in reducing venting of natural gas from our dry gas seal system due to its methane content?
We have actually developed a product, or let me take a step back. On a one of the neat thing about a centrifugal compressor is that the gas leakage is nicely captured at a flange at the end cap. So using these dry gas seals, there's basically one point at the compressor where this gas leakage can leave the compressor. So we can capture that very easily. And Solar has developed a product that allows you to take that leaked gas and recompress it to use it either as a fuel gas or bring it back into the gas stream. So we can actually avoid methane leakages on these machines.
That's great, Rainer, a methane recapture system. Thank you for expanding on that. Let's go ahead and stay with dry gas seal system for a minute. Do all compressors have wet and dry, both seal systems available? And is it chosen by the customer whether dry or wet will be used?
When I think back, I think the last new compressor that we sold with wet seals was in the late 90s. And the reason why essentially the industry has moved to dry gas seals is that they are far more reliable. They show less leakage, and that refers back to the question, how can we reduce the amount of methane emissions on our compressor stations? With dry gas seals, you can do pressurized holes. So you don't have to blow the station down when you shut down the compressor. So therefore, you avoid that methane leakage. Solar still supports the machines that we build with wet seals. And there are compressor models where we still maintain wet seal designs, but all the new machines that we currently are selling come as a standard with dry gas seals.
Absolutely. Thanks for the clarity, Rainer. And thanks, Amir in Pakistan, for the question. Really appreciate that. Let's take another question from the audience. Rafael Bastos is asking us, is it possible to change or upgrade the full bundle and keep the original casing of the compressor?
Absolutely. That is essentially the concept that if your operating conditions over the years change massively, and sometimes, for example, on gas fields where you have a declining field, these conditions can change significantly. You can take the entire bundle out. You either build a completely new bundle, or you reduce the aerodynamic parts from the old bundle and add or subtract new parts. So you have all these options, but in all these cases, the casing stays the same. And that's also part of why we're very keen on standardizing things that allow us to have specified rotor length for a casing, so we can add and subtract impellers within that bearing span.
Great, Rainer. Thank you for that. I think we have time to do one more question. I'm going to hold on the hydrogen question until we get to that section, so keep thumbs upping it. We will get to it. This question, Rainer, is from Dharmesh Panchal. Thank you. Okay, so most of the compressor OEMs provide compressor performance in terms of polytropic process. However, Solar Turbines provides performance as adiabatic process. Can you please clarify the reason?
Dharmesh, thank you very much for the question. To start with, Solar certainly is happy to provide the performance of our machines, both based on the polytropic process or on the isentropic process, both in terms of efficiency and work. And I also want to highlight what I said earlier, that the amount of power that you consume for a specific operating point doesn't change, regardless of whether you compare that power to a polytropic or an isentropic process. One of the reasons why we actually like the isentropic process is that if you build a process, then the process variable will fully define the isentropic work. They will not define the polytropic work, because to define the polytropic work, you need to know the discharge temperature of the compressor, or you need to know the compressor efficiency. So when you start out with a let's say a plant layout, then you have from your plant design everything that allows you to calculate the isentropic efficiency and the isentropic work. But in order to calculate the polytropic work, you have to make additional assumptions. But again, if you would like to have a compressor performance with polytropic work and polytropic efficiency, we are well prepared to provide that.
Very good. Thanks for the clarity, Rainer, and I hope that answered the question of our audience member. We're at that time, Rainer, where we can move on to the next section. Thank you. Okay.
Thanks, Danielle. Okay, now in the next section, I want to explain a little bit on how this actually works, that we take mechanical work and we convert it into pressure and temperature rise in the gas. Because those of you who are familiar with reciprocating compressors, it's fairly straightforward. You trap gas in the cylinder, you squeeze the gas, you get more pressure, you get more temperature. On a centrifugal compressor, we actually have to deal with the aerodynamics, and so there are three principles we have to talk about. So essentially the energy transfer from the impeller to the fluid, the use of the centrifugal force, which specifically applies to centrifugal compressor, and then also the fact that you can actually exchange pressure and velocity. So let's start with that one actually first. If I have a spool piece where I reduce the pipe diameter, then essentially the gas flow velocity, or the gas velocity, will be higher at the outlet than at the inlet. On the other hand, the pressure will drop. So in that spool piece, I convert pressure and velocity. I can do that also the other way around with a spool piece where I go from a smaller diameter to a larger diameter. And actually, turbines and compressors actually use this principle. So you see here a typical turbine blade row, where you see that the area at the inlet is much bigger than the area at the outlet. So I accelerate the flow, I convert pressure into velocity. Whereas in a compressor, I have a smaller inlet area than outlet area. So I convert velocity into pressure. So at various parts through the machines, we will the designers make use of that principle. But that's just converting pressure that I already have into velocity, or vice versa. The energy transfer actually works as follows. If I take a gas and I run it through, let's say, a bent pipe, so where I basically force the gas from that direction into that direction, then one of the things that's going to happen is that that gas exerts a force on the pipe. So if I now have that pipe running in a rotating system, then I have a force times the distance, and that is work. So essentially, the general idea of energy transfer is that I force a gas from one direction into another direction. So that's basically what's happening in the impeller. And in fact, actually, the impeller is in a compressor the only place where I convert mechanical work into work in the gas. The only thing, though, is that at the exit of the impeller, my gas does not just have more pressure, it also has a higher velocity. And now here comes the diffuser, and I'm going to explain that with a parallel wall or vaneless diffuser. And it's simply that the through flow area here at the impeller exit is much smaller than the through flow area at the end of the diffuser. And so when you look at the picture here on the right, you see how that that increase in through flow area leads to a reduction in velocity and an increase in pressure. So in the diffuser, as a stationary component, I simply make use of the fact that I can exchange the velocity that I have with the pressure that I want. Now, the guy who came up with all of that was a Swiss mathematician and researcher. And actually, he came up with that for about 250 years ago. And he basically said, okay, the change in work, the enthalpy change, is essentially that change in direction that I force on the gas times the spinning velocity of the impeller or the blades. So basically, that's Euler's law. So the work is the change in circumferential velocity of the gas times the spinning speed of the impeller. And so that basically also means that the faster my machine runs, the more work I create. And again, I already mentioned that work is only transferred in the rotating part. So with that, then I have a compressor that allows me to convert mechanical work into enthalpy rise in the gas. Now, since I want to operate this machine such that I adjust it to different operating conditions, I need to control it. And there are a couple of different things. You can change the speed of the machine. You can have inlet guide vanes that vary their angle. If you have vanes in the diffuser, you can adjust them too, although it's very rarely done. You can throttle the gas at the inlet into the machine, or you can recycle the gas around the machine. And without going too many details, for each of these methods, you get a different operating map. But the key thing is, if I want to, for example, go from a certain design point and then I reduce the flow, then and I look at when I reduce the flow, how much power am I going to save? And I see that speed control is by far the most efficient way of adapting a compressor to different operating conditions. And you see, basically, recycle also allows you to adapt to a lot of different flows, but without the benefits of reducing the power. Throttling gives you a little bit power back. Guide vanes also allow you to adapt the compressor to different lower flows. But again, the speed control is by far the most efficient way of doing this. And so, because we drive our compressors with two-shaft gas turbines, or in most instances when we use electric motors, these are variable speed electric motors, we have the capability to essentially control our machines essentially by varying the speed of the compressor. And the map that you see here, which shows isentropic head versus actual inlet flow, that's basically a map that shows how the machine behaves at different operating speeds, and also shows that essentially how the efficiency of the machine changes for different operating points. But in general terms, the faster you spin it, the more work you get imparted, but also the more flow goes through the machine. I've shown this, and by the way, just to come back to the earlier question, we also produce these maps for isentropic head and for polytropic head. There are a number of other maps. I'm showing just one here that essentially shows the pressure ratio over the machine and the flow. There are a number of different maps. The only thing is that, except for the map that I first showed, that has either isentropic or polytropic head versus actual flow, all the other maps are strictly only for one set inlet condition. So as soon as you change the inlet conditions, you would have to change the map. So therefore, from an application standpoint, the head versus flow map is actually the most universal one. Now, I mentioned that we do speed control, but we also use a recycle system for avoiding surging the machine. Essentially, a well-defined surge control system allows you to operate a compressor all the way down to zero station flow by recycling enough gas from the discharge of the compressor to the suction of the compressor to keep the machine on that map that I had just showed. So the way it works is actually relatively simple. The compressor map is essentially programmed into the surge controller, and as soon as the machine gets too close to that surge line, and that can be verified by measuring temperatures, pressures, and the flow. So as soon as I get too close to my surge line, the controller gradually opens the recycle valve and keeps the machine from surging. So that's the general idea. And again, this is simply used as a system to avoid surge when the machine is forced to operate at very low flows. Now, the other question that often comes up is, so what makes that compressor operate at a specific point if I change the speed? And that really depends on the system around the compressor. If you have a pipeline, the more flow you want to pump through the pipeline, the more pressure drops you have in that pipeline. So therefore, the pressure ratio in the station goes up. So that's, for example, that line A. But there are other applications where the pressure ratio is less sensible to flow, or there are applications where you essentially run the machine along a constant power line. So you see that a lot, for example, for storage withdrawal applications. The key thing in all of that is that the system around the machine determines the suction and the discharge pressure that the compressor sees. And then, based on the available power or the speed that the machine is set at, the compressor reacts to these conditions by flowing a certain amount of gas. And this is actually a very powerful concept. I was at a compressor station actually last week where we essentially used these concepts to operate the machines that we wanted to test at specific operating conditions, simply by manipulating the conditions that the system around the compressor imposed on it. And I think now we're again at the point where we have time for some questions.
Yes, we are, Rainer. Thank you. And once again, you're right on time. For the audience, just a quick reminder, there is a link now to the poll that you see live in front of you. The question that we're interested in is, which industry are you in? So here we have a majority so far from the midstream industry. A fair amount from upstream, a little bit from downstream. Good to see. Also from the university and academia space. So keep this coming, and let's go ahead and leave this up, Will, for a little bit longer while I ask a couple questions before we give the share back to Reiner. Okay, Reiner. Hey, and everybody, thank you so much for the questions. If you could, if you do want us to get back to you and we haven't been able to get to your question, please remember to put your contact information and we'll follow up. Okay, so let's take a question from Bill Reiner. What is the typical overhaul cycle for these compressor packages?
Well, the compressor really does not have a specific overhaul cycle. If you run the machine with clean gas and you don't damage the machine, there is no particular overhaul required. The overhaul cycles are typically determined by the drivers, or in some industries, you overhaul your machines because you overhaul the entire plant at a certain time.
Makes sense, Reiner. Let's talk about compressors in the sense of maybe efficiency degradation then. So there is an anonymous question from the audience. Is there an efficient way to measure the actual performance of the compressor to the design criteria to determine if there is any efficiency degradation?
Yes, there is. In fact, actually, we use the same principle on our control system, but what you fundamentally do is you measure the suction pressure, the discharge pressure, the suction temperature, and the discharge temperature. You determine what your gas composition is, and you measure the flow that goes through the machine. And in most compressors, most modern compressor stations, you can do this online, but if not, you may have to install some additional instrumentation. So with that data, you can actually calculate the isentropic or polytropic head that the machine is generating, and you can determine the actual head that it's generating, and you determine the flow. So now you can take the compressor map that practically any manufacturer will give you, either in a paper form or in a digital form, and then you look where on the map am I operating and what's the predicted efficiency at that point. And then I compare that with my measured numbers. Now, if I do that on regular intervals, and it doesn't really matter whether I'm exactly always at the same point, then I may be able to detect whether the machine is deteriorating versus its original prediction or not. Slight caution here, all these test numbers have a certain amount of test uncertainty. So if your numbers are 1% or 2% off, that could very well be the accuracy of your measurement, and it's not necessarily real deterioration of the machine. But if you monitor that over a certain period of time, then you get a very good picture on how your machine behaves in terms of performance degradation.
All right, Reiner. Yeah, that very much helps. Thank you so much for speaking to that. Okay, we're going to take another live question from our audience member, Shirkin Eshraghi from PG&E. Thank you so much. The question here, Reiner, is it healthy for any compressor to pass the surge line during a fast stop? Would this type of momentarily surge damage the compressor blades?
We try to design our systems that we avoid surging the machine momentarily during fast shutdowns. I would be lying, though, if I were to say it never happens. Now, a centrifugal compressor is a very sturdy machine. So unlike an axial compressor where you can actually damage the compressor even if these surges happens 1 or 2 times, you will not damage the centrifugal compressor if you just surge it once during shutdown. What you do, though, is that especially if you do it too often, things like clearances will open. There are a number of seals in the machine that over time, if you do it too often, you may see an impact of a performance. But if it just happens once or twice, that should not be a problem.
Gotcha. Thanks for the clarity and the guidance, Reiner, on that one, and good question from the audience. Okay, just as a wrap up here, the poll is looking pretty consistent. The majority of the audience members are from the midstream industry, and we can go ahead and hand the screen share back to you, Reiner, and get us back to your content. Thank you. And we still see the poll, just as a FYI.
Okay, should be back.
We're back, Reiner. Thank you.
Okay, so now you may wonder, how do I size these machines? If you have a given project where you know the operating conditions, how do I come up with the size of the machine to use? Well, we'll start out in very generic terms. Power is mass flow times work. So the mass flow, once I know the inlet density, which is determined by the inlet pressure, I know the actual flow, and the actual flow actually determines the physical compressor size. So if you have a lot of ACFM, it's going to be a physically big compressor. If you have very little ACFM, it's going to be a small compressor. So it may be that you only have a few hundred ACFMs, then it's like that rotor that I showed earlier, for that 7.5-inch rotor. If you have 10,000 or 12,000 ACFM, it's going to be a bigger one, probably like that rotor the big rotor that I showed earlier. Now the work is basically isentropic head divided by efficiency. And the amount of work, I know I can get a certain amount of work per impeller. So that essentially tells me how many impellers do I need and at what speed do I need to run them. And then the next question is between the compressor size, the impellers, and the speed. Does that match the driver speed? So if I have a gas turbine where the power turbine wants to spin at 7,000 RPM and my initial gas for the compressor gets me to, let's say, 8,000 or 9,000 RPM, I have to pick a bigger compressor to match the driver speed. And actually, Solar provides a sizing tool that's online that allows to actually very quickly get from pressures, temperatures, gas composition, and standard flows to things like isentropic or polytropic head and actual flow. And so once you do that, and this just shows an example, here you have the pressures and the standard flow and the gas and suction temperature. The program very fast tells you the isentropic or polytropic head and the volumetric flow rate. Now, what am I doing with this? Well, if you, for example, happen to have a compressor already and you have a compressor map, then you can, with this simple calculation, and just remember here, I'm at about 20,000 feet of head and about a little over 6,000 ACFM. So now you take your head versus flow map, and you look up for the isentropic head, and you take the flow, and now you know my compressor will operate right here. It should run a little under 9,000 RPM, and it should have an efficiency of about 86% or so. Okay, so the combination of these two tools allows you actually pretty precise determinations on what your machine is actually doing, or if you simply want to size the machine to give you a rough idea on how big the machine is going to be and how much power it's going to consume. Now, when we actually work on projects, we often have to deal with multiple operating points, and then it's a question of optimizing the staging to meet certain operating conditions. And so, for example, the blue staging would allow to operate on all the operating points. But the red staging, if you mostly operate here, is more efficient than the blue staging, but you would have to recycle 4.1. So that's the trade-offs that you do during the sizing of the machine. There is often the concern that centrifugal compressors are not easily adaptable to different operating conditions. And that's sort of a bit of a myth, probably coming from the fact that a lot of the early machines were constant speed machines that are indeed not very flexible, but with a variable speed machine, the adaptation to changing operating conditions is actually quite simple. So we take here a machine that was designed for this operating point, and now let's see what's happening if the gas gets heavier. Well, the machine that's supposed to compress that gas to a certain discharge pressure with a heavier gas simply runs slower. There's really not much you need to do. The process control would take care of that automatically. Now, if the suction temperature is rising, the machine's just going to run a bit faster. If the suction pressure is rising, meaning the pressure ratio goes down, again, the machine's gonna go slower. And it really then depends on whether you want to maintain the same flow or whether you want to use up all your power. That then determines where on the map you're gonna operate that machine. Now, one of the things I talked a lot about compression of natural gas right now. Now, once things like CO2 and hydrogen enter the field, there are a few things that we need to consider. And first of all, both hydrogen and CO2 are gases. So the same principles that I explained earlier apply to the machines, no matter whether you compress hydrogen or whether you compress CO2. The key difference is that while CO2 is a very heavy gas with a low speed of sound, hydrogen is a very light gas that has a high speed of sound. And hydrogen actually has a very high heat capacity. CO2 has a relatively low heat capacity. And that basically means nothing else, but in order to maintain a certain pressure ratio, I need a lot of work with hydrogen, I need less work with CO2. If we, for example, take the operation in at a given pressure ratio, in this case, I just used 1.5. If you compress natural gas, you need a two-stage pipeline compressor. If you add hydrogen to that natural gas, you will have to put more work into the gas. The more hydrogen you have in the mixture, and that basically means I need more impellers. So I may need a machine with 6 or 7 impellers here. I may need 2 machines in series here in order to maintain my pressure ratio. That amount of work that determines the power that I need applies to any type of compressor. So what I'm describing here is not something that's strictly that's a problem with centrifugal compressors. That's simply the thermodynamics of compression. And that gets us to the next Q&A section.
Yes, thank you, Rainer. Happy to see you had closed that section with a bit about hydrogen. There has been a growing liking behavior from our audience around a special question around hydrogen. And I know you touched on the number of bodies based on the pressure ratio needed due to the composition, but are there any other special considerations the user needs to be aware of when compressing hydrogen? Can you expand on hydrogen a bit?
Well, when you compress hydrogen, at some point in time, you have to evaluate all the materials that are used in the compressor, because there are known concerns about hydrogen embrittlement, and of course that concern changes with the amount of hydrogen that's in the gas. And there's really not a general statement that I could make here, but if you consider running a existing compressor with increased amounts of hydrogen, you would have to ask the manufacturer to check the materials, check the type of seals that are used in the machine, and so on and so forth.
Great, Rainer. Material considerations makes sense. So still on gas composition topic, we have another question from the audience from Afaq Hussain in Pakistan. How does the gas composition play a vital role in designing and sizing of the compressor?
Yes, it does. The gas composition essentially determines how much work you have to put into the gas, basically how many impellers you need and how fast you have to run the compressor for a given suction and discharge pressure. So when you specify a project, you have to specify not just the suction and discharge pressure and the flow and the suction temperature, but you also have to specify the gas composition. Now, later in operation, the machine will easily accommodate changes in gas composition, but we need something to get to start the design with.
Thanks, Rainer. I appreciate that response to our audience member. So in a little bit connection back to our previous question regarding compressor efficiency, we have an anonymous question on at which stage or percentage the compressor performance deviates from the design should a restage be considered?
You know, this is mostly an economic question. And it's really more determined, for example, what's your cost of fuel gas or your cost of electricity, and actually that's probably the most frequently asked question. If I restage, can I increase the amount of gas that I'm producing? So does the restage essentially give me an economic advantage in my production effort? And that is actually one of the things that if things like that come up on your station, we'd be more than happy to help with that evaluation.
That's right. Thank you, Rainer. And that's a great point. The follow-up, reaching out to your district office to evaluate the needs of your equipment is certainly what we would recommend. Thank you, Rainer. Okay, we're going to get a little bit more technical, Rainer, and bring us back to choke. So this question comes in from Peter Johnson. Thank you. At certain times, due to gas demand, we need to operate in a choke condition for extended periods of time. This has resulted in impeller failure on some of the other machines from other OEMs. Is this a problem that Solar has seen on our own compressors?
I'm not aware of impeller failures due to extended operation in choke. You have to be aware, though, when you operate a machine into choke, you will, for example, see the axial thrust of the machine changing. So you may see, for example, higher thrust-bearing temperatures. Now, the machine or the control system protects you from overloading the thrust bearings because there are some temperature limits. And by the way, there are manufacturers who will specify a line on the map. It's usually referred to as stonewall or overload line that they do not want you to cross. So that is a discussion that you would have to have with specifically for a given compressor with the manufacturer who made that compressor.
Understood, Rainer. Thanks for expanding on that a bit, and Peter for the question. So similarly related, Rainer, to that choke line and the choke condition, if the centrifugal compressor is run near that choke condition, does it affect the compressor life over time? And thank you, Abdul Rauf, for the question.
No, it should not affect the life of the compressor, but one of the reasons why it's normally not a good idea to operate in choke permanently is that the efficiency of the machine drops significantly. So So it then becomes a question of economics, whether you want to restage the machine to avoid operating in very low efficiency and using more fuel gas than necessary, or actually being able to actually pump more gas through your station by having a compressor staging that's more optimized to these operating conditions.
Understood. Thanks, Rainer. I think we do have time for another question and gas composition related. Can a centrifugal compressor handle dirty gas like a reciprocating compressor can?
It can handle dirty gas. In fact, actually, since we don't have these very narrow valves that tend to be sort of the Achilles heel of a reciprocating compressor when you run on dirty gas. The thing though is you're usually better off when you clean up the gas, for example, by having a functioning separator on the suction side, because eventually solids or oily deposits will stick to the impellers, and eventually you will see a performance deterioration.
Understood. Thanks for the clarity, Rainer. And thank you for the question, Yevgeny, from our audience member. So with that, Rainer, we're going to go ahead and move back to your presentation. Thanks, everyone.
Thank you. Okay, so let's talk a bit about different configurations of compressors on packages. And that's in particular when you have to make a very high pressure ratio. You can put two compressor bodies in series driven by the same driver, or you can put multiple stages into a compressor body that has not two nozzles but four nozzles. So you can either do a straight through or compound type machine where you essentially come in with the gas, you do some compression, you bring the gas out, cool it, bring it back in, and then do the rest of the compression. Or you can do a back-to-back compressor where you bring the gas in here, bring it out here, you cool it, you bring it in for the other end and bring it out here. And the choice of these different configuration is often driven by the operating range, by the operating flexibility, in particular also thrust load concerns, the leakage between the stages, and things like that. And that's in particular an issue when you compare straight through and back-to-back machines. Because actually we did a study to compare the axial thrust balance when you move the machine from surge into choke for an inline machine with two sections. So you have one section here, then you bring the gas out here, cool it, bring it back in here, or with a back-to-back machine where the gas comes in here, comes out here, and then is re-entered into the casing on the other end for the rest of the compression. So we simply looked into how does the axial thrust change when I operate either concept with otherwise the same staging from surge to choke. And what we found is that actually you get far more changes in axial thrust. That's therefore much harder to control with the back-to-back machines compared to an inline machine, which was actually one of the reasons that led to our decision to essentially have our multi-section machines in an inline configuration. The other thing is, of course, when you look into situations where you have, for example, gas fields with declining suction pressure, there are often advantages actually having multi-bodies, because you can initially, for the lower pressure ratios, run a single machine, and then when the suction pressure drops and the pressure ratio goes up, you add a second body. And then you can also because when fields decline, also the flow will go down. So that then also allows for very effective ways of restaging the machines. And if you do it right, you actually may be able to reduce the majority of the impellers that you have in your machines, which makes the whole restaging effort very, very cost effective. Another type of question on configuration comes if you go into gas storage, where you essentially fill from a pipeline, you fill up a gas field. So that basically means that the pressure ratio, once you increase the gas in your storage facility, the pressure ratio will go up. And the challenge there is, so when you start filling the field, you have a low pressure ratio, but you have a certain amount of power. So you want to increase your flow. Whereas once you start filling the field, even with the same power, your flow will go down because more of your power, more of the work goes into, more of the power goes into the work. So we, for example, found it very advantageous to have two-body tandems here, where you stage the low pressure and the high pressure body somewhat different, but you can run them initially in parallel. And then when the pressure ratio goes up, you run them in series. And the reason why that actually usually works better with two bodies is because the thrust load management in a single body machine may become very difficult, especially, by the way, with back-to-back machines. And then, of course, you have configurations where a gas turbine drives a single compressor. That's a typical pipeline configuration. You may have configurations where you drive 3 compressor bodies through a gearbox. You have configurations with gearboxes between compressor bodies, and you have the option having single compressors with multiple sections. So that's sort of the typical configurations that we see for especially applications where you have a higher pressure ratio. I mentioned gearboxes a few times. They can be either between the driver and the train, but they can also be between, let's say, the first compressor and the second compressor, or the second compressor and the third compressor. And the gearboxes, in that sense, give you actually the opportunity to adapt the aerodynamics of the compressor better to the gas flows that you want to deal with in the individual sections. And then on the driver side, again, we have the gas turbines, the two-shaft for compressor drives. We always use two-shaft gas turbines because that gives us a very wide speed range for the compressors. We have electric motor drives with variable speed gearboxes. So variable speed gearboxes allows you to use a constant speed motor, and then the gearbox for constant input speed is able to vary the output speed into the compressor. We have electric motor drives with variable frequency drives, where the motor actually is capable of running over a range of speeds. And we are also looking into applications where actually the compressor can be driven either by a gas turbine or an electric motor on the same skid to take advantages of different costs of gas and electricity, or to optimize the emissions performance in a compressor station. So I guess with that, I hope I've given you in the time that was available a general idea on how does gas compression work in general. How do centrifugal compressors do that task of gas compression? How do we size compressors, and what different configurations of compressors and drivers are available? So I hope I didn't make it sound too difficult, because a lot of these things are actually relatively straightforward, and centrifugal compressors are actually very, very simple, very robust devices for gas compression. So with that, I hope we have time for a few more questions.
We absolutely do, Rainer, and you did not make it too difficult. You did a great job of condensing a lot of information in a short amount of time for our audience, and very well spoken. Thank you. I'm going to take a question real quick that came in earlier, but we do have plenty in the chat. As you were talking about the different configurations and the pressure ratio, so what would the max pressure ratio you can achieve with any given configuration?
The relation, first of all, the relationship between pressure ratio and work depends a little bit on the gas composition. So you saw that on the slide with, if I compress hydrogen, I need a lot of work to get a certain pressure ratio. Whereas, for example, if I compress CO2, I get actually a lot of pressure ratio with relatively little work. So for a natural gas compressor, I can get in a three-body tandem configuration, I can get a pressure ratio between maybe 25 or 30. And in order to achieve that high pressure ratio, and that's really the important part, I have to cool the gas at various parts of the compression process. For one thing, to limit the temperatures that I produce, and for another thing, because the intercooling actually allows me to reduce the power demand for that compression process.
Yes, thank you, Rainer. And there was an intercooler question in the audience list of questions. I think you just touched on it. Thank you. Okay, so another popular question that people would like answered comes from Fahad Aftab. Thank you so much for asking this. Rainer, what is our experience with performing compressor surge tests at site to optimize the position of the compressor surge line?
The issue is fundamentally that the way we test our machines in the factory, we have a very precise idea where that surge line is. So what you're doing at site is actually more determining the accuracy of your flow measurement instrumentation to know where you're relative to surge. And there are other ways, by the way, of doing that. So it again goes back to how often can I search my machine before I see any damage? And that's almost an unanswerable question. When we talk about surge tests at site, what we actually really do in general is that we try to move the machine to the point where it does not surge, but where we see that the head versus flow characteristic really starts to flatten out. So I would, for example, not recommend to surge especially a high pressure machine at full speed, full pressure at site. You also will have a lot of unhappy people on your compressor station. Not necessarily because not because you damaged the compressor, but it also adds a lot of wear on your station equipment. So we can verify the surge line of the machine at site without searching the machine.
Great guidance, Rainer. Thank you for commenting on that. A question here from the audience, and try to like rapid answer this one, Rainer, regarding the dry gas seal. What prevents gas leakage across the dry gas seal while the compressor is not turning and is pressurized?
Well, when I explained the principle of dry gas seals, when the compressor does not move, that spring that I talked about pushes the two seal faces together. Now, there will be a very small leakage, but it's significantly less than, for example, when the machine runs, and we capture that leakage in the primary vent. And again, we can either flare the gas or recompress the gas, depending on what the requirements at the compressor station are.
Great, quick answer. Thank you, Rainer. And for those on the audience, we actually just posted the link to our, management of fugitive methane emissions. That takes you right to our Solar Turbines website if you'd like to learn more. Thank you. So we are in the final minute of our webinar today. So I'm going to share my final slide with everybody. Reiner, congratulations on your book release. We're all very excited. Again, everybody that registered for this webinar will receive a digital copy, and we should be able to get back to you if you are the lucky recipient of one of the signed copies that we can send you, and we should let you know by the end of the week. Do remember to follow us on social media. As you can see, we have a number of platforms available here. We look very much forward to seeing you at future webinars. And Reiner, again, excellent job. Thank you again for your contributions. Thank you everybody on the line for joining us today. Do take care and stay safe. Thank you so much.
Thank you so much.